Good afternoon, everybody. Thank you for joining our research seminar of ReCAN-IP, High Dimensional Statistical Modeling Team. I'm Makoto from the High Dimensional Statistical Modeling Team. So today's speaker is Mr. Mathis Petrovich from France. I just want to briefly introduce Mathis. So Mathis is currently a PhD student at École de Ponts, ParisTech. So he's a first year PhD student to the school. And also he's also belongs to the Max Planck Institute, not belongs to, but he's also co-supervised by the researcher at the Max Planck Institute. So he's interested in the topics including human body analysis, computer vision, machine learning, deep learning, and optimal transport. His current research focus on action conditioned human motion generations. Okay, so then, so Mathis, please start your seminar.
Okay, thank you, Makoto, for your presentation. So I will present the topic of action conditioned 3D human motion synthesis with transformer VAE. So I will present this paper, which I did in collaboration with my supervisor, so Michael Black from the Max Planck Institute and Gul Varol for the École des Ponts. So before I present that, why dealing with humans and computer vision? So computer vision, you have humans are actors act a lot in computer vision in all your in all different area. In assisted living or self-driving cars, it is very useful to know exactly the behavior of humans, where they are located in space, for example, to avoid accidents or to help the best people. So human and computer vision, it's a very old computer vision problem. Even at the beginning of computers, you see some research on this topic. As you can see, this paper is from 1991 and already had some results with human body analysis. So we talk in the related work in all of that, I will talk about first on human modeling, because it is very important how to model humans. So even in within this review of 1999, you can see some different way of different paradigm of how to model humans. There is some non-model based method, and there is a model-based method. And even at this time, you can see that the volumetric model-based method are very popular. And in fact, it is this kind of method which are now state of the art and used widely. So in early days in human body modeling, people tried to fit some 2D structure, some rectangle or square, to approximate humans. As you can see on the middle, there is the joints based model, which are also used nowadays with open pose, for example. They also tried 3D geometric primitives with a combination of cylinders and sphere. This kind of model works well at their time, but was a little complex to optimize, especially the sphere one. But nowadays, we used more skin model. It's way more realistic, as you can see there, on the scape on the left, and more recently, simple on the right. The simple model, I will talk a bit more about it because this is what I use in in our project. And this also simple model are very used widely because they have some good properties. Especially, there is the simple representation, which can disentangle pose and shape. So the pose is defined by the rotation of the body relative to the kinematic tree. As you can see, the red point on the figure. So when there is a different pose, we act on the rotation of the body. and the shape will be the shape of the body is how tall you are or how fat you are. This is the morphology of the body. And so it didn't tackle the pose and shape. And so given one pose, you can change the shape and give realistic motion or realistic pose with another morphology. Then after the simple model, more recently, 2019, there is a SMPL-X model which appeared, which model both the end and the face, as you can see on the right in this image, which got more realistic models. Then we got also an iteration on simple recently, the star model, which fixed a lot of problems of simple, and this model is more accurate with the shape. And lastly, the last paper, which from 2020, they present GUM, a non-linear human model, because the other model were linear. This one used VAE inside, and so it is also working great. With all this kind of model, they are very useful because they give a good prior on the body shape when you are using them in other topics like human estimation on images. This is what I want to talk a bit right now. So there is several approaches. So from one image, you want to predict a body. So there is several methods. There is the regression method, which is a bottom-up approach. It's started from nothing. You want to predict the human directly. So this kind of method are usually fast, but not so accurate. And there is also the other way around, the top-down design, which is optimization method. It's given an initial guess. You will try to optimize the loss. So you will iterate on the optimization until you get a satisfactory result. So this is the two kind of approach they used in also in human estimation in images. The first paper which successfully predicts both human pose and human shape from a single image is SMPLify. So as you can see on the pink is the estimation of the human in the image. In this paper, it is an optimization-based method. First, they use deep cut CNN, so they use like a bottom-up approach, predict the 2D key points and a confidence value on the middle of the image, the figure, and then they optimize the good simple parameters to get the human on the right. So for the optimization, what they are doing, they do a minimization of 5 loss terms, 1 data term, which is a 2D distance with the predicted key points. They use also a shape prior and a 3 poses prior. One is unnatural knee and elbow bending, because you don't want the elbow to be in the opposite direction. They also train a pose prior, which is a mixture of Gaussian, and they use an interpenetration error. The interpenetration error is useful because it can disentangle some ambiguity, as you can see on the left without the approximation, the interpretation term, and on the right with the interpretation term. In this paper, they approximate the interpretation term with capsules because it was easier and faster to train. In this kind of method, you still have some problem, as you can see. If the joints are not well made, predicted, you will have some problems. After this method, recently we have the equivalent, the SMPL-X method, which is the same optimization method, same ID, but with the SMPL-X topology, with the face and the end. So in fact, this paper which create and use the last SMPL-X model. They also introduce a V-poser pose prior, which is a latent representation prior with variational autoencoder. They also introduce better collision penalizer, a gender classifier, and a new data set for evaluation. Now, let's go to some regression method. So given, like, without optimization, given nothing, just predict the simple pose. HMR is the first method which successfully did it. So in this paper, they use some encoder, which is a CNN networks and a regression network to predict pose, shape, and camera parameters. And they use as a GAN, a discriminator, which will look at real motion capture data and check if it's a real human or not. And by using this discriminator, HMR really gets good results. The first method which got good result with regression method. After that, there is few iteration, for example, spin, which is a bit, which they try to get both idea of regression optimization, given a CNN feature structure. They use a method which is called SMPLify. They are doing the SMPLify method in the loop of the training loop. And so the training objective is you want to predict the regress shape on the middle. You optimize it with SMPLify, and you want your CNN to predict the optimized shape instead of just the regress shape. So in this way, they greatly improve the results. Then you got some method. Yes.
I have one question. So for this method, do you need to have some pair data set, like input image and corresponding like human pose? Or you just need to have a bunch of like input images and bunch of human pose? There are no correspondence.
So here they supervise with 2D key points. And when they are computing the loss on it, they are reprojecting the joints, the key points on the image to get some information. So it's like pseudo ground truth. It's not, you don't have the optimize the shape, but you have some 2D key point from open pose, for example.
Okay, so therefore this is like supervised regression problem, right?
It's kind of supervised, but you don't have the data. You don't have the shape, the regression.
Oh yeah,
you just have the joint. It's like semi-supervised maybe.
Okay, thanks.
Welcome. Then after all of this kind of optimization, we have some the same kind of optimization for simple X body. You got your SMPLify was very expressive, so you have the face and ends, but it was very slow, 50 seconds to optimize. And HMR type is a regression method, which are very fast, but not very detailed. And so expose is the first method to get the face and the end with a regression method. In this work, I will not go into much detail, but they first regress a coarse estimate. And then given the crop of the face and the ends, they got from the rough estimate, they refine the ends and the ends. After that, so this is a very recent paper, which works very well. They look at the image and they found out that on spin and other kind of method, it's very sensitive to occlusion. When they did some occlusion on the face and on the end, for example, the results is modified a lot. And in their method, they want to be robust to that, and they succeeded, as you can see on the figure on the bottom. How they did it is they try on the 2D part branch, they try to regress part of the body, so to do some segmentation of the body, and given the segmentation, they are training an attention network which try to combine this information, all this kind of information, with this 3D body branch. And with all of this information, they are robust to occlusion, and they got the simple parameters, camera, viewpoint, translation, etc. So as you can see in this image, it's very accurate now. So it's a very good method. We have also a new method. This is ICCV, so this year, 2021. From one image, instead of just outputting one pose and one shape, they are outputting a distribution of human pose and shape. Why this is useful? Because when there is some ambiguity, you don't really know exactly. You don't have, sometimes you don't have much clue. It's like all these possibilities of the encoder are possible. And so how to use it? It's useful to do some regression. So you just take the argmax of the distribution. You get the regress 3D pose on the top. If you have 2D key points, so you have another clue in the image, you can take the encoded distribution as a clue to how to combine. So you can combine the 2D key points and this distribution to get the best one. And also you can do some multiple view fusion by fusioning some distribution. So this is a very recent paper. So I'll talk a bit about the human estimation in image. Let's see how it works on videos. So I will briefly talk about WIBE, which is human mesh and motion recovery. So here they try to leverage the fact that there is, in a video, you have a lot of clue. It's temporally consistent. So they extract features with CNN first. Then they do some GRU to aggregate some information to generate the sequence of simple pose and shape. And here they use a GAN-like architecture. On the right, you can see AMAS, which is archive of motion capture, which is more than 40 hours of motion capture with the same simple topology. So they can, you can have a precise ground truth or simple ground truth. And so given a sequence of WIBE and a sequence of AMAS, they train it in a GAN way to see if it's a realistic motion or not. And this PR helps a lot to get a good result. This was 2020, so we used this method for our project. I will talk a bit about it later. But now we have some iteration on it. You have a MEVA, which try to fix the bad acceleration of WIBE. But they are doing it by also having the CNN and GRU architecture on the left. But they use a variational motion estimator, PME, which the goal of that is to generate a coarse estimate of the movement. And then they use a motion residual regression to get back the details. And by doing this in a two-step, you will have less acceleration error in the coarse estimate. And so and also in the final output. Very recently, also ICCV 2021, you get the humor, which learn a dynamic latent space. So given one state in the latent space, you can encode the one step to train it, and then you can sample from x minus one a state. You can get the delta to get the next step. So it's like in a kind of force mechanism. And also the output state, there is a contact point on the fit, which will be very useful in some applications. Here, given this this latent space, which is very this latent space really understands the human motion, they can try to use it for getting with input observation given good results. As you can see on the left, you can have just some key points, not all the key points, and the latent space can help to get everything and the contact. And so this is very good for the contact. You can see also there and there. There is some video. Even when it's occluded in the sofa, the fits are consistent. And I want to talk a bit about frame-based method because, in fact, now, so I presented WIBE 2 minutes ago, but the PARE, the frame-based method, which is very recent. In fact, even if there is no information in, they don't use a video, it's just frame by frame. It works better than previous method, WIBE. So because we are doing way better method in frame-based. We will have also better method in web, and also the latest work, ProHMR, is also very good. It's a frame-based method, so there is no smoothing and nothing at all, and you can see the result is quite good. Now I will talk a bit about 3D human motion generation. So there is a lot of different ways to do motion generation. First, I will talk about unconstrained motion generation. So when it's unconstrained, a lot of time it can be just walking or running. There is no actionness. It's just there is no action. So one of the first work of doing it is from 2005. They are doing some automatic segmentation on the data, and they are doing a PCA in the Fourier domain. And you can see here what kind of results they got. So it's quite realistic for this working sequence, but it's very limited to this non-action. Then I talk about it in human motion estimation, but humor by design, it can be used for generation also. Even so, they train an initial player, and then by using humor iteratively, they can get the rest of the sequence. So on the left, you can see even on unseen body shape, it can give a realistic motion generation. So there is no action; they just do what they want. And on the right, given the same starting point, as you can see, the four of them are the same frame. Because it's a VAE, you can sample noise in it, and so given the same starting point, you will have diverse samples. There is a lot of different way of doing motion generation, and some work I use also music. So in this work, horeoMaster, it's a production-ready music-driven dance motion synthesis system. So it's I think it's a company which really did. It's given a music, so it's they extract some sound features, etc. They want to predict human motion which dance to this music. So I suggest you to look at the result because I think it's very impressive, and the design of the architecture is very. There is a lot of different modules, very complicated, but at the end, they really mastered this problem. I will talk briefly about text condition 3D human generation and talk about language to pose. So in this work, they try to learn a joint latent space between the sequence of humans and a language sequence. Like for example, here in this, the sentence is a person walked in a circle, and you want to generate a realistic sequence of a man walking in a circle. To do that, they take the ground truth sentence and the ground truth, one of the ground truth sequence, and they do an embedding to a joint latent space, and they want this latent space, the point of the latent space, to be similar, to be close in this space. And if it's close to the space, by embedding after they learn a decoder of this space to output the sequence on the right. And so in this time, you can just take your English sentence, put in this space, and decode in the sequence space, and you will have quite the same as the input. Now let's talk about action condition 3D human motion generation. So this is a topic which I studied last year, and I was accepted to ICCV. So this is the inverse of action recognition, because action recognition, you get a sequence of motion and you want to output a label. Here, so you have a label and you want to output a sequence of motion which correspond to the label. So the goal is you have a sidekick action, for example, and you want to predict this kind of movement. So why we care about the action generation? If we want to teach an AI how human moves and the actions they can perform, we want to be sure that the computer understands well the concept of this action. What is this action? How humans think of the action? And so how to do it? It's possible to just teach a machine to generate the action and check if they are realistic or not. It's like if you have a baby and you want to teach it how to clap the hands, you can, if you want to be sure that the child understands it, you can just ask him, just clap your hand, and if they're clapping their hands, they understand the action. So by the same kind of thing, we want to be sure that computer understand an action. So you want the computer to generate action. So there is a very few literature on that. The most relevant is the action to motion, which is also condition generation of 3D human motions. Here, given a throw action, you want to generate several samples of it, motion 1, motion 2. So you want to have different way of doing the action and all the action being realistic. So in this method, yes?
Can I interrupt? So how do you give the information of the actions?
So in this action condition generation, you have a label, which is, so given a data set of 40 actions, for example, you will have labels corresponding to the action. So action 0, 1, 2, 3 to 39. And so it can be a one-hot encoding or just the integer. It's not unconstrained, it's not text-based, it's just given some label.
Okay, thanks.
This work is really the inverse of action recognition. Action recognition, usually you have also a list of labels.
I see. That makes sense. Thanks.
Welcome. So in action to motion, they are doing a frame level generator. So we just explained a bit on the bottom, the testing time. You have on the left, you have pt-1, so it's the state of the frame before. You have A, an action, and CT, the time of where we are in the action. And they use a variational autoencoder to learn some representation ZT. They also learn the pt-1. They also use pt-1 A and CT to get at the end the next step, pt. So by doing this, they're doing in a frame level. And so it's auto-regressive. They are putting something, getting another thing, etc., etc. So in our ROC, action condition 3D human motion synthesis with transform VAE, we tried to do it in differently. So we want instead having a sequence level generator. So we want to generate everything at once. We have this idea of doing a sequence level because we want to encode all. So the action information, it's a move. There is some duration, and so we want to compress all the information in a latent representation, which corresponds to the action. So we want everything to all the idea of action in one representation. So the general structure of our generator, we start from a random vector Z, which is a sequence level random vector, action category, and a duration. And we want our generator to generate a sequence of simple poses. So we choose a simple poses because at the end, when we have a sequence of simple poses, we can choose the shape we want, simple shape. We can choose a male, female, or some body fat. We can choose whatever. And then we can combine with the simple layer, we can get the simple vertices. So the blue person you saw and you will see, it's the output, final output sequence of simple vertices. So we use some data sets from monocular estimates. So they are not very, I explain. So we use a USTC, which is a 40 action data set with 40 actions, and NTU 13, which is a subset of NTU 120. So this subset was extracted in the action to motion paper. So we use it for comparison. As you can see on the right, you have on the top jumping jacks, and on the bottom from NTU drinking action. So this is kind of input we have. And so we use, from these RGB videos, we use WIBE, the method I explained earlier, to estimate the simple poses. And by doing so, we'll get like pseudo ground truth, which is real simple poses. So please note that these poses are quite noisy because the estimation method is not perfect. So our ground truth is a little bit noisy, but we want our model to handle it and try to understand something from it. So our approach is a sequence level rational autoencoder. So given a real simple poses and a label, the action category, we want to squeeze all the simple poses given an action to a latent space Z. One vector, so real simple poses, you have a sequence of size T, for example, and the encoder has no time information, it's just one vector. And then at this time, and then the decoder part, you have given this Z and a label and a time duration you want. We want the decoder to unsqueeze all this information and get the single and get back the single of simple poses. And so for the VAE, we have several goals. We want the latent space to be smooth, so we want to have a structure of the latent space. And we want also the single poses to be as close as possible to the input. So it's a reconstruction term. So this is the real architecture of actor. So it's an action condition transformer VAE. We name it actor. And so it's in this way. On the left, we have, maybe I can put my cursor. Can you see the red cursor?
Yes.
Okay, great. So here we start from a sequence of poses, P1, PT, which is the rotation of the body, so simple poses. A sequence of T simple poses. We first linear project it to some space, latent space. And here, at the same idea of VIT, so vision transformer, VIT, we prepend the input of the transformer with some hyperparameters, which are learnable. So mu A and sigma A are tokens which are hyperparameters, so they are learnable. And so we get one, so this set of mu and sigma token, we learn them for all the action. We have a set of mu and sigma. So we prepend it to that. And then on the output of transformer encoder, we extract the mu and sigma, which is a distribution parameter of the Gaussian latent space, which correspond to the mu and sigma token. So this trick was used in this kind of trick was used in BERT and in VIT to get the classifier. But here, one of the contributions of this paper is to use it with variational autoencoder to extract mu and sigma. And given mu and sigma, with the reparameterization trick, you can get the Z, the latent vector Z, which can be simple also in generation time. And then for the decoder, given the action you want to, given the action and the Z, we add the action information in like a bias term to like shift the latent space, and then we use a transformer decoder, but not autoregressively like in regular transformer. We use it in one step, so it's just a one-time prediction. We use positional encoding on the bottom, and we use the in a multi-head attention, we use the information of the latent space to get the representation, which with a linear projection, we get the simple sequence of simple poses. And then at the end, we can compute the vertices with some shape. So we use several loss terms. We use KL loss, which is to have a smooth latent space. We want the latent space to be similar to a Gaussian with mean 0 and identity sigma. And also, we use L2 norm for the simple poses. So we use 6D rotation because we found it works better than other rotation and other type of rotation representation. And we also use this term, which is LV, which is a loss on the L2 norm of the vertices from the input and the output. And we found this term, which very useful to get great results. So by talking about results, this is some qualitative ones. So you can see the description of the bottom, and you can see realistic action, which are simple from the latent space. So there is a huge variety of action in the USTC. You have a lot of gym actions, and they're working great. If we sample in this latent space, we can sample a lot of different noise in this space. And we found out that there is a very good diversity in our samples. As you can see in the standing toe touches, depending where we sample in the latent space, you can have one standing toe or two, for example. You can see here there is one, and here two, and also a lot of different way of doing this action. Same for Cyclic. We found out that there is the model learned to do it in both legs and in a lot of different ways. So we did some architecture ablation and found out that our transformer works great, and it works better than GRU and fully connected. And also the mu token and sigma token helps to have good results. So here for the metrics, we use same action to motion. We use we train action recognition network to get the accuracy metric and on the generated samples. And we also use it to get the FID by extracting features like the last layer of the action recognition network, and also the diversity and multimodality, which correspond to how diverse samples are, and multimodality is how diverse given an action the samples are. Here, I will show you some ablation over the losses. So here you can see the monster shape on the left is in fact because we learn only, we don't put a loss on poses. So inside the representation inside the network does not really know where the rotation is. So as you can see, the joint is good on the right. The corresponding joint is good, but the rotation is not very good because we does not constrain it. If we use only rotation, we find out that there is some motion which are freezing in time, so they are not doing anything. So this was an issue solved by mostly by the LV loss, so loss on vertices. And if we use only the loss on vertices, but we don't put a loss on the poses, the rotation, we found some unrealistic shoulder rotation, as you can see on these two videos, which are not very well. So with this result, we get the state of the art in action condition motion generation by difference to action to motion and other papers. By talking about comparison, this is some comparison with action to motion. On the left, it's action to motion. So they are outputting only joints. And for their visualization, they have to optimize another simple parameter, which is not trivial. And in our case, we are outputting directly the simple mesh. This is Cyclic. As you can see also, in the methods, they are a little bit shaky, and ours are more smooth and a little bit more realistic. So to get our things works good, we had some parameter that matters. The weight of the KL loss. So we add all these loss term, the reconstruction term and KL loss, and we found out that the KL loss is what has to be properly designed. So we tested a lot of value, but in fact, the value which works best was the 10 of the power of -5, for the weight of the chaos, which is very low, but it was the way to, thanks to that, it was working. Also, the rotation representation was a little bit also useful with axis angle representation does not work well, for example. We found out that the number of transformer layer was also useful, as when we add more transformer layer, it works better. And also to train it, we use a mini batch size of 20. And if I added more a larger batch size, it did not converge well. So the batch size was also important. So here in all the experiments I showed you before, it was all the time with a fixed duration of like 60 frames, as you can see in the red curve on the left. But we tried to put more frames or less frame from 40 to 120 frames. But when we train with only 60 duration, and as expected, the accuracy drop and the FID go larger, which is not good. And so so we try to train this network with random size duration from 60 to 100. But if we only train from 60 to 100 with random frame, it didn't converge well. So we had to first train it as on the left, and then fine-tune it from 60 to 100 frames. And by doing so, it works great. And also, by asking more frames, it still give good results, and everything is more stable. Like talking about that, for generating variable durations, I will show you the same action, the same noise, but we just ask more time of it or less time of it. For 40 frames on the left, it is too few frames, so the move will not finish. But as we augment the number of frames from 60 to 100, it will be slower and slower to get up. You will see. And so all the moves are realistic, but it's the scale of doing the action is different. Here on butt kicks, you will see that as we ask more frames, there is more cycles. And this was a interesting way of using more frames. And because we have a sequence level VAE, we can do some interpolation in the latent space of actions. And so here we take an action, a noise vector. We take minus the noise vector and we interpolate between z and minus z in the latent space. And we found some interesting results. For example, the shake fist action starts from the right end. And as far as we go from the latent space from one point to the other point, we will go from the left end. And so the latent space really captures the essence of the movement. Same for a punching action. We go from the standing action to the sitting one in a smooth way in the latent space. And for the throw, you will see that as far as we go from one point to the other point, we will go from lower to higher throw. In this model, because we have the real data is very noisy, as I told you before, by encoding and decoding through our latent space, we can get more smooth action. As you can see, the left motion on the noisy motion on the left, and our encoded decoded on the right, which is more is less jittery. You can also see this example and this one. So our results smooth a bit the motion and so it gets more realistic. So we can also talk about the simple topology, but given the same generated sequence of pose, instead of just taking a random shape, you can choose the shape you want. Here we see the same sequence, and I change the body fat, and here I change the gender, and it also works great. But here, even if we change the shape, you can still have some mesh interpenetration because we does not constrain it. So here there is no loss term to prevent the collision. And so it can happen at the end to get this kind of behavior, not good. And also, we found that in some fine-grained movement, like head anti-clockwise circling, you can see on the left, it can be thought as a noise by our model. And so some of this kind of action, they are not, the generation are just frozen in time. It converges with a frozen state because it can be thought as a noise. Also, because of the monocular estimate, it's very hard to get precise distance to the camera because there is a lot of ambiguity. And so the root translation, by given this noisy data, the root translation are often very bad in our generation, as you can see on this one on the left and high knee running on the right. So what next for action condition generation? Maybe by looking at humor rich work rate, maybe it's good to get realistic contacts, to get realistic motions. It can be also useful to use a more expressive model. Instead of just simple, we can use simple H with at the end or simple X, the body, ends, and facial expression. And also, it should be great to have a transition between action, like picking up something, then sitting, then doing something. So I have everything coherent in time. Also, we can also think about two actions at the same time, like sitting down and waving the hands at the same time, which is also a hard problem. And it could be good to have also a text-based generator for this problem. And we can condition with the text. Also, it can be good to, so there is a lot of works on human closing, and there was a lot of progress recently. This paper is 2021. And so by giving close to the human avatar, it can be more realistic for the human eyes. So thank you for your attention, and tell me if you have any questions.
Okay. Thank you for the talk. It's very, very nice. And so from the participants, do you have any questions? If you have any questions, please put your questions to the chat box, or you can just feel free to ask the questions. For now, I have some questions for the computation. Like, actually, how long does it take to train the model? Like, is that easy or?
So to train the model, it depends on the data set, but it takes like 20 hours to 30 hours. It depends on where you want to stop.
Okay.
And it depends on the data set. For optimization, it was, yeah, I just try with a fixed learning rate with like, I didn't fine tune a lot the learning rate. So maybe if you fine tune it more, it will be faster to convert. But it was okay to optimize. It works.
Okay, so it takes for 20 hours for one data set, one model.
One data set, yes.
Okay, so yeah, so just for curious, like for writing paper, like if it takes like 20 hours for one model, it takes a lot of time. So do you have any clusters to compute or?
Yes, so for this project, I use the Janvet clusters, which is from France. It's a supercomputer where you can submit some jobs.
Okay, very nice.
You can also, here in this project, so I have some question from Dinesh. It's on GPU, but it's on one GPU, and it does not take much GPU power since we have a small batch size of 20. And so it takes maybe 3 or 4 gigabytes of GPU. And you can train it on only one GPU. So I have a question. What is key difference between conditional GAN? Could you explain why VAE is better for this task? So in fact, VAE and GAN, you have both models are powerful, and you can choose any of them. In this paper, we choose VAE. because we want to have the encoder and the decoder. Usually in GAN you don't really have the encoder, just the decoder part. And for the VAE also, usually it's easier to train than GAN. And we tried it and it works like that. So we didn't try it with GAN. Maybe it can also work. I have a question. What about noise? How sensitive is your model to the quality of images or video? So the noise, so it's also, it depends of, so you have the quality of images and video, which are important to get the real simple poses. But in fact, it also depends of the noise given the estimation, the human motion estimation, because it gives you not real ground truth. So in fact, we found out that our model give a reasonable motion, smooth motion, even if the motion estimation and the images are not great in quality. So for future works, there is now a data set. So I talked about AMAS, which is more than 40 hours of motion capture data. So they are very, they are like perfect data. And here there is a team which released Babel maybe 2 or 3 months ago, which is a data set which they take the AMAS data set and they annotate almost all the frame of this data set. So now by using Babel data, for example, you will have way more, better data for input to the model.
So do you have any other questions? Yeah, we can just wait a few more minutes or then. And for now, I think I had another questions. Okay, so I have another question. So in your talk, you said this is for to understand the machine learning model is working great or something like that, right? For the applications. So do you have any other applications for of this approach? Like,
sure. Here in this work, we also present one use cases in action recognition. Like given this type of generator, you can generate infinity amount of data, and so maybe we can use this model to learn better action recognition model, as you will have better data. Also, as the Humor did in the paper, maybe you can also use this this as a prior to get better human motion estimation. For example, if somebody is doing a bicycle, even if one of the feet is occluded by the bicycle, if you know that if he is doing a bicycle, you know that the feet will be like in the opposite direction. And so maybe given this type of model and as a prior, you will have a better estimate of the motion. It can be also in graphics to help a designer to generate motion for cinema. It has some other application.
Nice.
By the way, if you want to check on the website, I also release the code online, so you can check if you are interested in.
Okay. Thanks. So from the audience, do you have any other questions? Okay, if not, let's thank the speaker again. Thank you, Mathis.
Thank you.
Okay, so then this is the end of seminar. And so again, so this seminar will be uploaded to the Regressing AIP YouTube channel. So yeah, if you're interested, please check the YouTube channel as well. Okay, thank you very much.